Okay, so before we start on the next 3 units in the 2020 parade of Introduction to Engineering remote assignments, I think it would be a good idea if I went over the general idea behind something called sine, cosine, that's an E there, and tangent. Now, having the stuff I'm going to go over here, you actually don't have to know it to do the problems I'm going to give you, but it will make it make more sense, and I think therefore will make it a little easier. But this right here is just a nice to know going forward. So here's what we're going to do. You actually might have the ability to, I'm going to share this with you, to print this piece of paper. And therefore you could actually measure and follow along with me. If you can't, it's no big deal. You just follow along and listen to what I'm saying. If you are going to use this piece of paper, though, and follow along with me, my desk is a mess. I'm looking for my scissors. What you can do is at the top, you can cut this off and use it like a ruler. So, for example, there we go. Now, it's not too hard to count. Each one of these squares is 10 of these little blocks. So this isn't difficult. If I say that this side from here to here is 10, 20, 30, 40, 50, is 70. All right. That's a right angle. So we could say this, this whole thing down here is 70 blocks long. From here to here. So, and then this is, you'll notice, half of that, 10, 20, 35. So this is 35 from here to here. And like I said, this is a right triangle. Sine, cosine, tangent are functions that apply, at least in this scenario, to right triangles. Now, the reason the ruler comes in handy is what if I wanted to measure this? It's a little harder to do that. So I could line this up and count the number of blocks here. So, for example, I could go 10, 20, 30, 40, 50, 60, 70, 80, a little more than 80, maybe 80 and a half, something like that. So I could do something like that. And that would be the hypotenuse from here to here. So if you want to measure with me as you go along, fine. If not, just listen up. Okay, so for this right triangle, I'm going to choose this angle down here. It doesn't really matter which one we choose, but I'll choose this one here. And if you've picked up, you will pick up the letter, I don't know what to call it, the symbol we use for angles is oftentimes something called theta. It's a Greek letter. It's a circle with a horizontal line through it. And then oftentimes the other angle might be called phi or phi. I can't remember which one it is. That's just a circle with a vertical line through it. It's kind of like we use x for numbers that aren't angles, the distances and so forth. So this we'll use as our missing angle, so to speak. All right. So what I'm interested in is this, for this triangle, what happens if I just take, let's pick 2 of these numbers. Let's say this number over here, the one that is, and this is going to become an important phrase, opposite of this angle. So if this was a strangely built room, and you were let into this room and told to stand here, and somebody asked you what is opposite you, what wall is opposite, it would be this one. The person standing here, of course, would say this is their opposite wall. And if you were standing at the right angle, then the hypotenuse would be the opposite. But depending on where you are, there is always going to be an opposite. There's always going to be a hypotenuse, and that's the same for everybody, the longest one, and an adjacent side. But for now, let's just look at this side over here, not even worry about what it's named. It's 35, divided by the sine, the size of this side here. Right. So if I do, ready, we'll label these. For this angle, we'll go ahead and label this. This is the adjacent side. This is the opposite side, and of course this has to be the hypotenuse. So if I look at the opposite over the hypotenuse. I want to do the opposite over the hypotenuse. You'll be clear in a second. So that would be 35 over 80.5. All right, that would represent opposite divided by hypotenuse. What about, let's do another pair. Let's do the adjacent side divided by the hypotenuse. So if I look at adjacent side divided by the hypotenuse, that would be 70 divided by 80.5. And the one we haven't done yet, let's do opposite over adjacent. And that would be 35 over 70. All right, big deal. Right now, I'm not. There's no miracles or anything. Nothing special about this. Just setting us up. The one I really want to look at is this, because I've set this up to be 35 over 70. So that's 0.5, right? That's a half. Well, I'll write it as 1/2. Or 0.5. Let's find these two. So dig out my calculator. There we go. Got this one handy. And I'm going to do 70 divided by 80.5. 70 divided by 80.5. And if you can't see it, I get 0.8696. And if I do the opposite over the hypotenuse, 35 divided by 80.5, I get 0.4348, rounded to 4 places. All right, big deal. Whatever. So far, a pointless conversation, I understand. Here's the interesting part. What about a completely, not completely, but what about a somewhat different triangle? What if I create a triangle that is a little bit different? Not completely different. In fact, we would describe them as similar triangles. What if I do this? What if I describe this triangle? This pink one. Now, I just picked out at random. If we take some quick measurements, notice the angle didn't change. Neither did this angle, by the way. In fact, these two angles have to add up to 90, right? Because if this is 90, and all the angles add up to 180 in a triangle, so these two haven't changed either. I could even write this here to be more consistent. But the sides have changed, the lengths of the sides. So this one, for example, is 10, 20, 30, 40, 50. This is now 60 from there to there. And this is now 10, 20, 30. Interesting. And the other one is 10, 20, 30, 40, 50, 60, say about 69, I suppose. Right. 69. Not 6.9, but 69. Well, what I want to look at is what if we do this same set of combinations? What if we find the opposite over the hypotenuse for this new pink triangle? What if I do 30 divided by 69? Interestingly enough, I get, so if I do it for the pink, where I do 30 divided by 69, I get 0.4348. I get the exact same number. Because the ratio, the proportion hasn't changed. It's easiest to see in the 30 and the 60, isn't it? If we look at this last one, the opposite over the adjacent, that's 30 over 60. That's still obviously going to be 0.5. And so maybe we'll focus on that one for a second because it's easiest to see. So no matter what I do, even if I change colors, to green, and I look at, say, this, I'd still have 1, 2, 30, and 15, which would be still 15 over 30, still going to be a half. And you can imagine all the other proportions are going to stay the same. So wait a second. That means this angle has a set of numbers, like this one, this 0.4348, or half, or 0.8696, that go with it, because the angle never changed. The triangle might change in scale, but the angle doesn't. And so for that angle, which by the way turns out to be, I believe, 20, no, this is where I could cheat a little bit. About 26.6 degrees. So this angle, which happens to be 26.6 degrees, I could say for that angle, there are these 3 ratios that are always going to be connected to that angle. Because if I change this angle a little bit, I change these ratios, and that does not come out, the opposite over adjacent is no longer going to be half if I change that angle a little bit. So what we needed, or what math people, they found this was kind of interesting and important. So they needed names for these ratios. Not these numbers, but these. And so they named them. I don't know where the names came from. I wasn't at that meeting. It was long before I was born. But here's what we know. So if you're standing at an angle, the opposite side from you, divided by the hypotenuse, the opposite over the hypotenuse, carries the name sine. And every angle has its own value for the sine. 26.6 has 0.4348. If you have a different angle, for example, 30, a 30-degree angle, that actually will be 0.5, strangely enough. The adjacent over the hypotenuse, so this over the hypotenuse, is called the cosine. And the opposite over the adjacent, that ratio is called the tangent. And that means that what this all means is that if you know the angle and one side, you can find the other sides. At least one of them, definitely, and then you probably use the Pythagorean theorem for the other. But you can all you need is an angle and a side, and knowing that it's a right triangle, of course. And you can find stuff out. And that's very useful. What we're going to look at is how to solve problems using each of these individually. Right? But that's where they come from. So like I said, you don't have to have this in order to do what we're about to be told. You just need to know for now. In fact, let's finish this up with this. This is probably the most important part. You just need to know that the sine is the opposite over the hypotenuse. That the cosine is the adjacent side over the hypotenuse, and that the tangent is the opposite over the adjacent, or sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent is opposite over adjacent. And for years, actually, this may have come around after I was in high school because they didn't teach me this, but for years, students have been using this, Sohcahtoa. 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 If you remember these letters in that phrase, then so, sine opposite over hypotenuse, cosine is adjacent over hypotenuse, and toa, tangent, is opposite over adjacent. It is a way of remembering which names go with which pairs and the order in which they go. So this is not a bad thing to know. Okay, let's move on and let's work with the sine.